You've been lied to about electricity your entire life. They told you electrons flow through wires like tiny marbles, little particles bouncing along, carrying charge from one end to the other. A nice, simple story, but it's wrong. Electrons don't move through wires like that, not even close. That's a classical fairy tale. The truth is far stranger, and this changes everything. To see why, let's do a thought experiment. Imagine a single electron in a copper wire. If electrons were classical particles, you could track its position over time, like watching a baseball fly through the air. You'd see it bumping along, gradually making its way from one end to the other. A straightforward trajectory. But try to track an electron in a real wire, and suddenly things get fuzzy, literally. You'll see a smeared out cloud, a haze of probability. The electron seems to be in many places at once, spreading out like a wave. What happened to our trusty little particle? Welcome to the quantum world. In the quantum realm, electrons aren't solid marbles. They're ethereal waves. Waves of what? Probability. The electron's position is inherently uncertain, described by a wave function that tells you the likelihood of finding it at any given point. It's everywhere and nowhere at the same time. But it gets even more disturbing. According to quantum field theory, the electron isn't just a standalone object. It's an excitation of the electron field permeating all of space, a ripple in an omnipresent ocean. What we call the electron is just a localized vibration, a concentrated wiggle. So when you hook up a battery to a wire, you're not pushing individual electrons through like peas in a straw. You're sending a pulse through the electron field, a synchronized shimmy of countless overlapping waves, all choreographed by the strict rules of quantum electrodynamics. Classical intuition breaks down completely. The tidy notion of electrons as discrete particles moving in straight lines is an illusion, a mirage that evaporates under the unforgiving light of quantum reality. The electron's position at any instant is fundamentally unknowable. Trying to pin it down is like trying to trap a ghost. It slips through your fingers, lost in quantum fog. Heisenberg's uncertainty principle sees to that. But here's the really mind-bending part. Despite the fuzziness, electrons still produce the reliable, predictable currents that power our world. Somehow, the synchronized dance of countless quantum waves conspires to create an orderly flow. The microscopic madness gives rise to macroscopic sanity. This is the central scandal of quantum mechanics. Predictable outcomes emerging from fundamentally unpredictable components. A clockwork machine built out of pure probability. And it's not just a quirk of electrons, it's a basic feature of reality. The classical world of crisp certainty is a lie. Beneath the facade of solidity is a churning sea of quantum maybes. The concrete is an illusion, the fog is real. And this is just the beginning. Because if a humble electron can shatter our intuition so utterly, what bigger revelations await us in the quantum depths? How else might the true machinery of the cosmos defy our naive expectations? Before we go any deeper, I need to ask you something. If you're here for comfort, this isn't the channel for you. But if you're here for truth, or even when it's unsettling, take a second to support this mission. Hit like, subscribe, and leave a comment telling me what part of reality shocked you most. Every interaction tells the algorithm that depth matters more than distraction, and that thinking clearly still has value. If you want to keep tearing apart reality with me episode after episode, make sure you're following. We're just getting started. The story of electrons gets even stranger. It's not just that they're spread out probability waves instead of neat little particles. No, the real magic happens when electrons meet. You see, electrons aren't just fuzzy loners sloshing through wires. They're entangled in an intricate web of quantum connections. A subatomic social network where each electron's behavior is inextricably linked to the others. Entanglement is the spooky heart of quantum mechanics. It's the reason Einstein famously derided the theory as spooky action at a distance. But as bizarre as it seems, entanglement is very real, and it utterly demolishes our classical notions of causality and independence. Imagine two electrons that have interacted in the past. Perhaps they were born in the same atom, or passed each other in a wire. Quantum theory says these electrons can become entangled, their quantum states intertwined like lovers in a dance. Here's where it gets really eerie. Once entangled, these electrons stay connected no matter how far apart they may wander. A quantum bond stretches between them, transcending space itself. Measure the spin of one electron, and you instantly know the spin of the other, even if it's light years away. It's as if they're still whispering to each other across the cosmos, locked in a secret communion that defies the speed of light. But before you get too romantic, remember, this isn't a storybook connection. It's raw physics. There's no sentimentality in the equations, no favoritism in the Schrödinger equation. Entanglement is a cold, hard fact of the quantum world. And it gets even more disturbing. The mathematics of quantum mechanics says that entanglement isn't just a two-particle affair. In principle, vast webs of particles can be entangled in dizzyingly complex ways, their quantum states interwoven in a tapestry of correlation. When you look at the electrons in a wire this way, classical notions like current and voltage start to feel like crude approximations. Cartoon sketches of a richer, stranger reality where particles dance in delicate quantum synchrony. The classical idea of electrons as independent entities bouncing through wires like billiard balls is a laughable simplification. It's like trying to understand a symphony by studying a single violin. In the quantum realm, everything is interconnected. The crisp lines between objects blur into a foggy haze of probability and correlation. The universe is not a collection of distinct things, but a holistic web of quantum relationships. And here's the kicker. This isn't just true for electrons. It's a fundamental feature of quantum physics. From photons to quarks, the building blocks of nature are less like solid bricks and more like ethereal threads in a cosmic tapestry. The implications are staggering. If the basic components of reality are so thoroughly entangled, so deeply enmeshed in a web of correlation, what does that mean for us? Are we too just patterns in the quantum fabric, knots in a grander, stranger tapestry? These are the kinds of questions that keep physicists up at night. Because in a world where electrons are fuzzy, probability waves, and entanglement is the norm, anything seems possible. But don't take my word for it. Dive into the equations yourself. Grapple with the quantum weirdness firsthand. And if you start to feel reality unraveling around you, don't worry. That's how you know you're doing physics right. Follow the channel for the next mind-bending installment. Trust me, we're just warming up. The quantum rabbit hole goes a lot deeper. You're probably feeling pretty unsettled right now. The solid ground of classical physics is crumbling beneath your feet, and the quantum world is looking more like a psychedelic fever dream than a sober description of reality. But don't worry, it gets weirder. We've seen how electrons are better described as probability waves than particles, and how they can become entangled in vast quantum networks. But the real crown jewel of quantum strangeness is the infamous double slit experiment. Picture this. You're firing electrons at a screen with two slits in it. Common sense and classical physics says the electrons should behave like tiny bullets, going through one slit or the other and making two neat bands on the detector screen. But when you actually do this experiment, something bizarre happens. Instead of two bands, you get an interference pattern, a striped tapestry of light and dark that looks suspiciously like the pattern you get when waves overlap. It's as if each electron is going through both slits at once, interfering with itself like a wave. But how can a single electron, a supposedly indivisible particle, be in two places at the same time? Welcome to the paradox at the heart of quantum mechanics. Some physicists tried to explain this by supposing that maybe the electrons were somehow splitting in two, with each half going through a different slit. But the mathematics of quantum mechanics says otherwise. When you crunch the numbers, you find that the interference pattern only makes sense if each electron is literally going through both slits simultaneously. Not splitting in two, but somehow existing in a superposition of two different paths. It's a bit like Schrodinger's famous cat trapped in a box with a poison that may or may not have been released. According to quantum theory, until you open the box and look, the cat is somehow both alive and dead at the same time. Its fate entangled with the quantum state of the poison. With the double slit experiment, each electron is like a miniature Schrodinger's cat. It's not just in two places at once, it's in a superposition of two or more different states. A quantum blur of possibilities. And it gets stranger. If you try to peek at which slit the electron is going through, if you set up a detector at the slits to catch the electron in the act, the interference pattern disappears. It's as if the electron knows it's being watched and changes its behavior accordingly. This is the heart of the quantum measurement problem. The act of observing a quantum system seems to fundamentally change its behavior. It's like the universe is a coy magician, always one step ahead of our attempts to pin it down. Some interpretations of quantum mechanics, like the Copenhagen interpretation, say that the electron doesn't actually have a definite position until we measure it. That the act of measurement itself forces the electron to choose a path, collapsing the wave function and destroying the interference pattern. Others, like the many worlds interpretation, propose that every quantum possibility is actually realized in a branching multiverse, that there's a parallel world for every path the electron could take, and we just happen to find ourselves in one particular branch. These are deep metaphysical waters, and physicists are still arguing about the best way to interpret the quantum formalism. But one thing is clear. The double slit experiment reveals a fundamentally non-classical reality. A world where particles can be waves, where cats can be alive and dead, and where the act of observation is somehow tangled up with the reality being observed. And remember, this isn't just abstract philosophizing. The double slit experiment has been done countless times with electrons, photons, even molecules. The results are unambiguous. The quantum world is irreducibly strange. But it gets even more mind-bending. Because if particles can be in multiple places at once, entangled in vast quantum networks, what does that mean for the nature of space itself? Is the space we inhabit just another quantum illusion? Brace yourself, because we're about to take a dive into the twisted geometries of quantum spacetime. And trust me, after this, your conception of reality will never be the same. Follow the channel for the thrilling conclusion of our quantum odyssey. In the final chapter, we'll see how this strange world of quantum mechanics is forcing us to rethink the very fabric of the cosmos. You won't want to miss it. You might think we've reached the limits of quantum strangeness. Electrons that behave like waves, entanglement that defies space and time, cats that are alive and dead at the same time. Surely, reality can't get any weirder than that. Oh, but it can, and it does. Enter the holographic principle. This mind-bending idea, born from the unlikely marriage of quantum mechanics and gravity, suggests that the three-dimensional space we inhabit might be a grand illusion, a projection from a two-dimensional quantum reality that underlies it all. Imagine a hologram on a credit card. The card itself is flat, two-dimensional. But when you shine a light on it, a three-dimensional image emerges, popping out as if by magic. The depth, the solidity, the very three-dimensionality of the image is a trick of light and information encoded on a flat surface. Now imagine that the entire universe is like that hologram, that the quantum bits, or qubits, that make up the fundamental fabric of reality are encoded on a distant two-dimensional surface, like cosmic information painted on the sky. And what we experience as three-dimensional space, with all its depth and volume and apparent physicality, is just a holographic projection of this deeper, flatter reality. It sounds like the stuff of science fiction, I know. But the holographic principle is as serious as physics gets. It emerged from the study of black holes, those cosmic sinkholes where gravity runs amok and even light can't escape. When physicists tried to understand what happens to information when it falls into a black hole, they ran into a paradox. Quantum mechanics, with its stubborn insistence that information can never be lost, seemed to clash with general relativity's prediction that anything that crosses a black hole's event horizon is gone forever, swallowed by the singularity at the center. To resolve this apparent contradiction, physicists had to do something radical. They had to imagine that all the information inside a black hole is somehow encoded on its two-dimensional event horizon. Like a cosmic hard drive, the horizon stores everything that's fallen in flattened, compressed quantum form. But the story doesn't stop there, because if the physics of black holes implies that three-dimensional information can be encoded on a two-dimensional surface, could the same principle apply to the universe as a whole? Could it be that the vast three-dimensional cosmos we see around us, with its planets and stars and galaxies stretching out to infinity, is just a holographic projection, a shadow cast by a flatter deeper reality. That when we look up at the night sky, we're really staring at a cosmic screen, pixels of information masquerading as points of light. This is the dizzying vista opened up by the holographic principle. A view of reality where depth is an illusion, where the true action plays out on a distant flatland we can never directly see, but which somehow encodes everything we experience. And it gets stranger still, because in a holographic universe, even time itself might be an emergent illusion. Some physicists suspect that at the deepest level of reality, time doesn't exist at all. That the flow of moments, the arrow of time that we take for granted, is just another holographic projection, a byproduct of the way information is encoded on that distant two-dimensional surface. In this view, what we call time is just a way of organizing information, a story we tell ourselves to make sense of the patterns and correlations we observe. But at the fundamental level, reality is timeless, a static tapestry of entangled quantum states with no inherent notion of past or future. If your head is spinning at this point, don't worry, you're in good company. The idea of a holographic, timeless universe is enough to make even the most seasoned physicist's brain hurt. But as strange as it sounds, this is where the cutting edge of theoretical physics is taking us. The holographic principle is still a work in progress, a tantalizing hint at a deeper theory of quantum gravity that remains to be fully articulated. But it's a powerful idea, one that's already reshaping our understanding of space, time, and the nature of reality itself. So the next time you look up at the stars, remember, you might just be looking at a hologram, a flattened shadow of a deeper quantum reality. And the flow of time that seems so immutable, so inescapable, that might just be an illusion too, a trick of perception in a universe where past and future are merely stories we tell. But don't despair, because in a holographic universe, every piece of the hologram contains information about the whole. Every quantum bit, every entangled electron and dancing photon is a microcosm of the entire cosmos. In a sense, you contain the universe, and the universe contains you. And that, my friend, is a story worth telling. A quantum epic of information and illusion, where reality is stranger and more marvelous than we ever dared to dream. So keep asking the big questions. Keep pushing at the boundaries of the known. Because in a universe as weird and wonderful as this one, who knows what revelations await us in the quantum depths? If the holographic principle has blown your mind, if the idea of a timeless, two-dimensional universe has shaken your reality, good. That's how you know you're doing physics. Follow this channel for more mind-melting excursions into the quantum wonderland. Trust me, the adventure is just beginning. If you made it this far, you're part of the rare few who refuse easy answers and actually want the truth. If you want to keep dismantling reality with me and exploring the deeper structure behind everything we think we understand, make sure you're subscribed. Leave a comment with the question that's still bothering you, and let's keep pushing into the silence together.